It started out with graphene and then it went to functions. I'm doing FOIL to solve X. Next is the expressions. Now I have to see if X is equal to or greater than 3.
Hey guys, let's go over lesson 3.8, reference for experiments. Our learning targets. After this lesson, you should be able to outline or draw an experiment that uses a completely randomized design. Number 2, explain the concept of statistically significant in the context of an experiment. And learning target number 3, use simulation, that's like the computer making projections, to determine if the difference between the two means or two proportions in an experiment is statistically significant. Learning target number 1, in a completely randomized design, the experimental units are assigned to the treatments completely by chance. Number 2, random assignment to treatments is absolutely essential in any experiment. And 3, there is no requirement that treatment groups be exactly the same size, although there are some statistical advantages. If they are equal in size. So I want to talk about some vocabulary words in this below. This is a completely random design. This is an example. And I just want to annotate a couple of things that we see here. These are called our experimental units. These are our 20 volunteer students. And here you have the randomization is what I want to this one. So experimental units in orange. Okay, when you split them into your two groups, here we are exercising our control. It's two things, control. You're also controlling, how much caffeine they give them, but you're also in both of these, you're also doing something called replication. Because if you have the same amount of caffeine and no caffeine, and then you do the 10 students in one group, 10 students in the other, someone else can replicate or redo your experiment. And then over here, we have a comparison. Okay. All right, let's go down to our first example here. To mint or not to mint. In Mr. Tyson's class, 30 students volunteered to participate in an experiment to determine if chewing mint during a test will increase their score on that test. Mr. Tyson will provide mint gum for half the students, while the other half will not chew gum. The same test will be given to every student. He will look at the test scores to see if chewing mint during a test increased their scores. Okay, I want you to go ahead and complete 1A and 1F. That should be a review. So basically fill in the box and then press play when you're ready. All right, so let's go ahead and name the experimental units or subjects. These are the volunteer students. Uh, 1B, what is the researcher comparing? Chewing mint, chew mint versus no mint. What is our explanatory variable? What is explaining? It is the mint. What is the response variable? How can you see how people respond in this situation? It's going to be the test scores. Okay, what's the treatment being used? It's the same thing here. Chew mint and no mint. Oops, forgot to see there. And what's missing in this assignment? Mr. Tyson is forgetting, I don't know if you saw it, randomization. Okay, so let's go ahead and draw this out. We have our 30 volunteer students. I used cyan or light blue before. Volunteer students. And then from here, this is where we should be doing our randomization, our random assignment. To help you, that's just really our dare. I'm going to use the digits 1 to 30, and then I'll use pieces of paper. You don't have to write these details below. It's just kind of helping you understand those details you've done in the past. And then I put in a hat, and basically the first 10 that I pick will go into one of our 2 groups. So we'll call this one group 1. And this is 15 students. And this is group 2, 15 students. And what is our treatment? Oops, ran out of space. Here's a cool thing about technology, kind of. I can't resize it yet. What's our treatment? Our treatment here, treatment 1, is that these students will get mint gum. And then treatment number 2, these will get no gum. And then the end, dark blue, we said. Here we got to do the comparison, so we will compare. But what on their test though? Their mean, the average, the mean test scores. So this is our example of a completely randomized design. Let's go on to page 2. All right, on page 2, we're going to explain the concept of statistically significance in the context of an experiment. Number 1, before making any firm conclusions, we must account for possible differences in responses that can occur due only to the random assignment. Pick a brighter color, sorry. 2, when the observed difference in responses between the groups in an experiment is too large to be explained by chance variation in the random assignment, we say that the result is statistically significant. So it's not caused by the chance in our random assignment. It's measurable. And we're going to use the abbreviation for our notes, SS. Okay. So I wanted to explain the word significance. In everyday 2A, everyday language, significance means usually something big. Like I got a significant pay raise. I remember at Jamba Juice, my first pay raise was 10 cents an hour. That was big. Some people got 0 and some got 5 cents. I think I got the max, 10 cents. Or, you know, maybe someone has a big pay raise and they got a $20,000 annual pay raise increase. That is big. That is significant to that person. So let's just write pay as my example. And then it can also be important. Important, the word significance. There was a significant temperature is my example. Temperature change in the Arctic, and the glaciers are melting, and the temperature change was 0.1 degrees Fahrenheit. Although the 0.1 is not a lot, it's not big, it is significant in the world because it might cause flooding. But this is not the same. Let's try that again. This is not the same as statistically significant. 2B, everyday language. So statistically significant means we have evidence. We have evidence that the result we see in the sample also exists in the population. This is a big idea of statistics where we can't get everybody in the population, so we take samples. But if we see a difference in the evidence in our sample, then we can say that is called statistically significant. Okay? All right, look at this dot plot here. I think this was an example of the Botox. I don't know. Maybe it was the Botox. I don't know. But you have two groups here. And in the two groups, they were split. Their treatments were maybe they were asked to be active, like, 1 hour of stretching and exercise. And then the second treatment was inactive. Remember, the dot plots is one individual. One dot is one person. And then they are showing us improvement in pain rating. So this is no change. And over here, this would be like big change. Okay, so this dot plot is showing the improvement in pain rating for subjects receiving both active and inactive, magnets, not exercise, magnets. The researchers in this study determined that the difference of the mean improvements was, yes, statistically significant. Why you can count the number that had major improvements, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 people said that there was significant improvement in their pain ratings. In other words, a difference in mean improvement in this picture, 14.4, was too large to occur simply due to chance variability, right? Like different people can tolerate different types of pain. But those magnets we're trying to show is like important, so use magnets. Okay, example number 2. Are you still watching cartoons? In the alternative example from lessons 3.1, 3.7, you learned that about an experiment to determine if watching a fast-paced cartoon, watching the educational cartoon, or drawing had an effect on the brain function of 4-year-old children. 60 children were randomly assigned to one of these treatments. One of the executive functions, which is decision-making, task at the end of the study was a delay of gratification. If children could wait long enough, they could have 10 pieces of snack food. But if they couldn't wait long enough, they would only get 2 pieces of snack food. The response variable was how long in seconds the children were able to wait. 2A, outline a completely randomized design for this experiment. Okay, you draw that flow map. Press pause and then press play when you're ready. All right, so we got 60 children. Four-year-olds, and they were placed into, I think, 3 groups. Fast-paced, 20 go into the fast-paced cartoon. Watching an educational cartoon. So 20 go into the watching educational cartoon. And I'm just doing this for notes purposes, is just using the abbreviations, but if you had to use this for a quiz or test or your homeworks, do not use abbreviations because I won't know unless you defined it. And then the third group was drawing. I kind of simplify this because this represents the groups, this represents the treatment, and just like I forgot, in here you can put randomization, SRS, simple random sample. How do you split up the 20? That's the DARE. Okay, then afterwards, they wanted to know the wait time, they compared the wait times. That's right, compare on top. Right, you're kind of telling the kid if you can delay, you get 10 pieces. If you can't wait, then you get 2 pieces. But that's what they were comparing, is the wait times. That was the response variables. That was this box right there. Okay, let's do 2B. The average waiting time for children in the educational group was 257.20 seconds, compared to the average of 146.15 seconds for the fast pace. The difference, the 111 second difference, was found to be statistically significant. Explain what it means that the difference was statistically significant. So they basically just took the 257.20 and they subtracted it from the other group, and then they got that number 111.05. So they don't have to do any subtraction, but I want to show you that because you're actually going to have to do that later on. So we're just supposed to be here explaining what the Statistically significance means in context, the difference, which is 111.05 seconds in the average waiting time in these two groups was, so this difference, that number above, was too large. To be due only to chance variation. In the random assignments to treatments. Let me give you guys another example why, okay? So let's pretend you have like crazy girl or crazy boy in one of those groups. You're like, wow, that crazy kid's never going to wait. Doesn't matter if you gave them fast-paced cartoons or they watch the educational cartoon or they do drawing. That crazy kid is just not going to wait. They're just going to snatch up those snacks and they're going to wait like 3 seconds. So if I have one of those crazy kids and I randomly assign to one of the groups, you're saying that might change the numbers. But we're saying that it doesn't. It's not the crazy kid and that random assignment. It's actually what they're doing, the treatment, the red, pink, and blue, the drawing, educational, or the fast-paced cartoons. Okay, 2C. Change the color here. The average wait time for children in the educational group, where's the educational group? That was pink, was 257.20 seconds compared to the 242 seconds in the drawing group. The 15.2 second difference was not found to be statistically significant. Explain what this means. That the difference was not statistically significant. So again, they took 242 and then they subtracted it from 257 up here, 0.20, and then they subtracted those and then they got 15.2. So the difference was 15.2, but that number is not really large compared to 111. Does that make sense? So we could say the difference, which was 15.2 seconds in the average wait time so basically just repeating what's above in these two groups was small. We're saying this number, 15.2, was small enough that it could be due to chance variation in the random assignments to treatments. So if I have that crazy kid who's randomly assigned, well, you're saying it doesn't matter. We're saying it's actually the treatment. It's actually watching the educational cartoon or the drawing has made little kids wait longer to get more of the candy. Rather, the fast-paced one kind of encouraged kids. Maybe it's like hurry, franticking. You're just moving really fast, and it makes the kids move faster. Okay. All right, let's move on now. All right, let's go over learning target number 3 on page 3, use simulation. So we can use simulation to determine if the difference in two statistics is significant. We use the one quantitative variable applet to do 100 trials of the simulation described in the activity. So, do you remember Mr. Lecow's caffeine experiment? Some students were given caffeine, some were given not, and then they were testing their blood pressure. The dot plot shows that getting a difference of 1.2 isn't that unusual. In the 100 trials, so there's 100 dots because n equals 100, so there's 100 dots. In our simulation, only 19 of those, which is in this box right here, had a pulse rate more than 1.2. We obtained a difference in the 1.2 or more simply due to chance variation in the random assignment. Because a difference of 1.2 or greater is somewhat likely to occur by chance alone, the results in Mr. Lecow's class is not statistically significant. If you had like 30 or 40 or 50, that would be a lot more, but 19 is not a lot. All right, let's apply this. Do you need another Botox treatment? Here are the results for the Botox experiment. Remember, they gave them Botox was meant for cosmetic surgeries, but they actually found out if you gave it, it could possibly reduce back pain relief. Or the placebo, or the fake, was saline, which is basically like salt water. Calculate the difference in proportions. Okay, let's review what proportions is. Proportions is just a fraction, which you can get as a decimal. Okay, so the difference in calculate the difference in proportions who experience pain relief in Botox. Let's use a different color here. So Botox, in our Botox, how many of those experienced pain relief? So the pain relief is here, so that would be 10 over how many people had the Botox, 15. And you'll subtract that by those who experience in the saline, so my orange box here, that would be 3 out of 16. You can just put that one in your calculator, 10 divided by 15. That will give you, if you rounded, 0.667, subtracted by 3 divided by 16 in your calculator, you get 0.1875, and then we get an answer of 0.4792. Remember, that's a decimal, so if you wanted a percent, you would have 47.92%. Let me show you how the calculator can actually solve that. Just put those in parentheses, 10 divided by 15 minus 3 divided by 16. So you don't have to do anything like subtracting or adding fractions. And then if that happens, you can, let's see, math, turn it into a decimal, and that's the same number. Okay? Okay. Let's do this next question. 100 trials of simulation were performed to see differences in proportions would occur due only to chance variation in the random assignment, assuming that the type of injection, Botox or saline, doesn't matter. That is, 13 patients who would have had pain relief So let me just help you track. The 13 that they're talking about is up here. And the 18 who had no pain relief, here in blue, no matter what treatment they would receive, would randomly assign to two groups, 15 to the Botox and 16 to the saline. Just as the real experiment. Use the results of the simulation in the dot plot below to determine if the difference in proportions for part A is statistically significant. Explain your reasoning. Okay, so then let's do this number. Let's highlight it. I wanted pink. Come back to pink. This number, 47.92. Okay, so then you're going to look on your graph over here on the simulation. Remember, each dot, they ran a simulation. And then the question is, how many times do you have anything higher than 0.4792? How many is that? That's just 2. So let's write our findings. Because a difference of 0.4792 or higher occurred how many times? What did we circle over here? 2 times. Occurred only 2 times in 100 in the simulation. The difference, meaning those who take the real or the fake, is what? Yes or no? Is statistically significant. Can't spell. It is extremely unlikely to get a difference this big simply due to chance variation in the random assignment. All right, and those 2 examples of the difference in the caffeine and blood pressure rate, this one. So that was, we said, 19 out of 100 trials. Let's do this one. So when is it statistically significant? And I just made this chart. The last problem we said, yes, it's statistically significant. In the last problem, this was 2 out of 100. So 2 out of 100 gives me 2 2%. And this is less than, I'm going to throw out a number, 5%. 5%. In the problem above, we said it was not statistically significant because it was 19 out of 100, which is 19%. And that number is not smaller than 5%. So what can we say? This one can be due to chance. Due to chance. And we're saying this one is not by chance. This is a very difficult concept. We're kind of just touching in brief. I'm not using some more complicated terms like null hypothesis, alternative hypothesis, but that's kind of like the big idea. Okay, so on page 4, you have this example of, does fish oil affect your blood pressure? I'm really interested about this one because I always thought about taking fish oil. Is it healthy? I want you to try it and then go ahead and press play to see your answers. Okay, first it tells us to outline a completely randomized design for this experiment. To see if fish oil can help reduce blood pressures, males with blood pressure were recruited and randomly assigned to different treatments. 7 of the men were randomly assigned to a 4-week diet that included fish oil. So N equals 7, and then you got FO, fish oil. That was one group. Okay. 7 other men were assigned to a 4-week diet that included mixtures of oils that approximated the types of fat in the typical oil. So I'm just going to say N equals 7, no FO, no fish oil. Okay, so we add those together, then your experimental units are 14 men. And then here you have, so it's experimental units, just trying to use some vocab. Here we should have had some kind of SRS. And then you have the groups, the 7 men, and then the treatment was the fish oil or not fish oil. Okay, let's just finish this. And it says, at the end of the 4 weeks, each volunteer's blood pressure was measured again, and the reduction of the diastolic blood pressure was recorded. These reductions are shown in the table. Note that a negative value means that the subject's blood pressure increased. Okay, so then the end result is compare change in blood pressure. You can note that you could have put the treatment in separate boxes if you wanted to. That would have looked a little bit cleaner. Okay, so what's the big idea? I just want to make sure you guys understood. A lot of it is context and understanding real life. And this is where your English history, everything really. So in a person, if your blood pressure is low, this is good. BP, blood pressure, is good. So if you have a high blood pressure, this is bad because your heart beats faster, like at resting point. So if I was just sitting here at my desk and my heart rate was really high, that means my heart is working really hard. It's probably because my arteries or my lungs could be clogged. I don't know. I'm just telling you the difference between good and bad. Okay. All right. 4B says calculate the mean reduction of each group. So now we have to calculate the mean. So we said the fish oil group. These are the numbers. So the fish oil group, we'll call this the average of X. So the average of X is just adding all those up divided by how many are in the group. divided by the 7. So the average for the fish oil group, 46 point over 7, so that gives me 6.57. And the units, they don't have for you, but I'll just put it in there, millimeters per HG. I don't know what that is. Okay, so that is something we need. Okay, so then the pink is the mixture group, or the non-fish oil. So y equals the mixed group, or the no fish oil group. So here I'm defining my variables. Now I'm just going to find the average, -6 plus 0 plus 1 plus 2 plus -3 or -3 minus 4 plus 2 divided by 7. You're going to get -1 point, what was the total? -8 over 7, which gives me -1.14. And we were saying that a negative number, a negative number means that it increased your blood pressure. Increasing your blood pressure, remember we said, was bad. Okay. All right. So now it tells us to calculate the difference in mean reduction. Now it tells us fish oil, so that would be the orange, 6.57 minus the negative 1.14. So if you do that, then the difference is 7.71. Okay. Now it's going to tell me the dot plot. 100 trials of simulation were performed to see what differences in means are likely to occur, due only to chance variation in the random assignment, assuming that the type of fish oil, fish or not oil, fish, doesn't matter. Use the results of the simulation below to determine if the differences in means from question 4C, should be 4C, is statistically significant. Explain the reason. Okay, so let's go and find 7.71. Okay, so let me use my pen here. So here is 7, and that number, 7.71, what color green? And anything higher than that, I'm going to assume that's like 2 of them, right? Would you guys agree? Okay, so this is 2, and really there's 100 dots, so 2 out of 100, okay? Now, look above. When you had a low number, such as the one in green there, 2 out of 100, this is less than 5%. This is not by chance. This is statistically significant. So let's write that. Because a difference of means of 7.71 millimeters or higher. Did it come up often or a little in the green box and the dot plots? How many times? It rarely occurred. So, or higher, rarely occurred in the simulation. Out of 100, which is like 2%. And is that number bigger or smaller than 5? It's smaller than 5. The difference is statistically significant. That's an it, is unlikely to get a difference it is unlikely to get a difference this big simply due to chance variation in the random assignment. All right, let's review what we learned. We learned in learning target number 1 to outline an experiment that uses completely randomized design. Number 2, explain the concept of statistically significant in the context of an experiment. And number 3, learning target number 3, use simulation in the computer to determine if the difference between the two means or proportions in an experiment is statistically significant, meaning that your p-value, they call it, those on the dot plot, it was a low percentage because it's we're saying that it's not due by chance. And so that is learning target 3.8, inference for experiments.
It started out with graphene and then it went to functions. I'm doing FOIL to solve X. Next is the expressions. Now I have to see if X is equal to or greater than 3. Now you make that point on the X-axis. Wait, was it a positive 3 or a negative 3?